Hello guys, in this video we're going to see how to design synchronous counters. Specifically, we will see how to design a 0 to 9 synchronous counter with a 7 segment display. Coming to prerequisites, this is a fairly advanced topic, so we expect you to be familiar with the following topics: Boolean algebra, K-maps, logic gates, combinational circuits, BCD system, and sequential elements. In sequential elements, you need to know how to write excitation tables for different flip-flops. Our objective is to learn how to design synchronous counters. We will see the step-by-step process for designing synchronous counters in general. We will also implement these steps in designing a 0 to 9 synchronous counter using JK flip-flops. We will also see a simulation of the circuit. So, how to design any synchronous counter in general? Step 1 is to decide the number of flip-flops. Step 2 is writing the excitation table for the selected flip-flop. And then step 3 is drawing the state diagram corresponding to the counter we are going to design and the characteristic table using the state diagram and the excitation table. And step 4, we use K-maps to obtain simplified equations. And then step 5, the final step is to draw the logic diagram or circuit diagram. Now let us see how we can use these steps to design a 0 to 9 synchronous counter. So step 1 is to decide the number of flip-flops. We can simply say the number of flip-flops required are decided by the number of bits required, that is the maximum bits the counter uses. In our case it will be 4 because the greatest number 9 is 1001, which uses 4 bits. We're going to use JK flip-flops for doing this. You may also use D or T flip-flops, it's not a problem. So step 2 is writing the excitation table. Since we chose JK flip-flops, we will be writing the excitation table for JK flip-flop. If you choose to use D or T flip-flop, you can write the excitation table for the corresponding flip-flops. Here Q and Q plus are the present and the next state correspondingly, and the J and K values are the corresponding values for Q and Q plus. For Q and Q plus being 0 and 0, J and K are 0 and don't care. For 0 and 1, they are 1 and don't care. For 1 and 0, it's don't care and 1. For 1 and 1, it's don't care and 0. Now, coming to step 3, drawing the state diagram. State diagram represents the order in which the states of counter occur. In our case, it starts with 0 and ends with 9. After finishing, it again goes to the first state, that is 0. So if you can observe here in the state diagram, it's starting with 0 0 0 0, which is the first state, and then it ends with 1 0 0 1, which is the last state, and after 1 0 0 1 it is again returning to 0 0 0 0. So this is how it goes on in a cycle. Now let us see how we can write the characteristic table. So if you see here, we have the excitation table from a previous slide, and then I'll explain how to write the characteristic table. So Q and Q plus are the present and the next states. J and K are the corresponding values. So as an example, if you take Q naught and Q naught plus, they are 0 and 1. In the excitation table, for Q and Q plus having 0 and 1, the J and K values are 1 and don't care. So here J naught and K naught are also 1 and don't care. And then if you see Q1 and Q1 plus, they're 0 0. So for Q and Q plus being 0 0 in the excitation table, we have J and K values 0 and don't care. So here we will write J1 and K1 to be 0 and don't care. This is how we will write the whole characteristic table. It is just lengthy, but it's easy. And now using the characteristic table, we will write K-maps. We take the present states, that is Q0, Q1, Q2 and Q3 to be the inputs, and J and K to be the outputs, and we use the characteristic table to write the K-maps as shown. We've got 8 K-maps in total. You may pause the video and check the K-maps with the characteristic table. Now for the final step, we draw the circuit diagram from the expressions obtained. Just as you can see, this is just the combinational part from the expressions which we use to connect all the sequential elements. Now Arya will be explaining the BCD to 7 segment decoder circuit.
Now let us see how to design a BCD to 7 segment LED display decoder circuit. First of all, we will understand how a 7 segment LED display works. As the name suggests, there are 7 segments. Each segment is an LED named from A to G. There are two types of 7 segment displays, common cathode and common anode. For our purpose, we will be using common cathode. In common cathode display, each LED is connected to ground, so giving high voltage value makes the LED glow. You can see the detailed structure of the display system in the figure. For displaying each number, the LEDs are to be illuminated in a particular combination. You can see the diagram to understand how the combination work. Taking the BCD representation for each decimal number as inputs, we write the truth table as shown with the 7 segment out as outputs. Since the BCD system has only representation for 0 to 9, rest all are under don't care conditions. Now according to the truth table, we made the K maps as follows and get the Boolean equation as shown. You may pause the video and check the K maps with the truth table. Finally, using the Boolean equation, we construct the circuit as shown. Now let us see how we design the whole circuit for the 0 to 9 counter for simulation.
So, this is the simulation of the whole circuit. This is the clock. We have set clock time as 500 milliseconds, which means for every half second, the clock changes its value from high to low or low to high. The connections glowing in green color are high and the connections which are not glowing are low. You can see that the 7 segment display shows the counting from 0 to 9 as expected.